It's great to be here at ProMat. I'm Erik Nieves, CEO of +1 Robotics. Some of you know us. We're a software company making 3D and AI-powered vision that gives robots the hand-eye coordination they need to perform meaningful work in warehouses, distribution centers, couriers, etc. For the past 40 years, robots have been used to perform repetitive tasks in factories and manufacturing facilities the world over. And they've been very successful at that. But that's all they could do, was repetitive tasks. And when a robot encountered either an object it wasn't familiar with or a change in the process, a worker would need to enter the robot cell, address the issue, and fix the robot and get it back on track. But e-com and fulfillment and distribution, they're predicated on variability, the variability of the items passing through. And there isn't one size of brown box or padded mailer. It's an endless array of package shapes and sizes and items and SKUs that move through a warehouse. And there's thousands of new SKUs added daily. So the technology needed to image and process this high variability didn't exist 10 years ago. But the rate of technological innovation has made logistics robotics more accessible. And it's now companies beyond the big shippers and e-com. They're all accelerating plans to automate because warehouse operators are facing this critical juncture in which their growth is outstripping the availability of the labor around them. So today I wanted to talk to you about this path from traditional, robotics to this notion of, sort of semi-autonomous robots and the advancements that are made possible due to these improvements in the technology. To do that, I wanted to give just kind of a quick overview of industrial robotics. Prior to founding +1, I spent 25 years at Yaskawa, one of the largest industrial robot companies globally. So I've seen firsthand the evolution of this space over time. And when I say industrial robots, this is probably what you're thinking. Typical spot welding line in Detroit, 100, 200 robots on a line, all performing, spot welding of whatever you drove in here in today. This still remains one of the most important applications for industrial robotics. But I can tell you that every one of these robots is blind. Their benefit is in their endurance and in their ability to move a lot of mass quickly and with precision. But it can only handle a few different option codes as they roll down the line. Maybe the sedan, the two-door coupe, and the hatchback. But if you put a pickup truck frame in front of it, it won't know what to do. Because traditional robots are programmed for a task or a small set of tasks, and that's all they can do. But it was Gil Pratt, when he was still at DARPA, that wrote a paper where he proclaimed that there is a Cambrian explosion coming to robotics. And that has borne true. But if we think about the Cambrian explosion, right, the evolutionary biology, if you subscribe to that model, is that you had a sort of prime mover, and once the conditions were right, all of a sudden you had this great proliferation of creatures. And it was increased specialization, and it was lots of different types of morphologies. And that's what the Cambrian explosion means in terms of biology. But the same can be said of robotics. You see the prime mover here, Engelberger's first robot, the Unimate. And it was a pick-and-place robot, 50 years ago. But from that seed, once the environment was correct and suited, then you had this plethora of different robots and morphologies that grew out of that. This is what we mean by the Cambrian explosion of robotics. And, it kind of breaks into a couple of different major branches. One of them is mobile robots. You see a couple of examples of those here. Robots delivering your toothbrush that you forgot, at the hotel. Robots in retail facilities, distribution centers and such. Even mobile robots for electronics assembly. But the bulk of the robots in the explosion are arms. And, today you see all types of different arms. You've got 6-axis robots that are the traditional type. You've got kinematically redundant 7 degree of freedom robots. You've got a whole new domestic set of robot manufacturers in China now. Large robots, small robots, and safe robots. And that's where I want to spend a little bit of the time today, is in this notion of collaborative robots, because one of the main things that has grown out of the Cambrian explosion in manipulation is this notion of robots that are safe to be near, where proximity is possible between the robot and the person. As we talked about, in traditional robotics, the robots would be on one side of a guarding, and the people would be on the other side of the fence. And it wasn't that those spot welding robots were trying to break out of the zoo. It was that you needed to keep people from inadvertently entering their space because they were so powerful and so fast that they could cause real harm. But collaborative robots is this idea of a force-limited robot, a robot that by its nature is not capable of injuring a person in and of itself. So there's a couple of ways that you can achieve force-limited robots. One of them is intrinsically in the mechanics of the arm itself. Basically, you make the robot compliant. And then the other is in the control loop, where you can control the amount of force or torque that the motors are expending and therefore make the robots safe. And one of the benefits of this technology is their focus on ease of use. You'll notice that this operator is teaching the robot by actually grabbing it and moving it through the set of poses that he wants the robot to perform. In the end, these collaborative robots were built on a different premise. They worked under different constraints, meaning, what if I didn't have 3-phase power or 480 available in the facility? What kind of robot could I build if I just had a 110-volt wall outlet? Well, it would obviously be a smaller robot. It would be incapable of lugging a 150-pound spot welding gun, but 5, 10, 20 pounds? Sure. But that's a lot of applications, because we as people build our processes around our capabilities, and we're at about a 20-pound limit if we're going to do this day in and day out, hour after hour. And so what you saw then is lots of these collaborative robots appearing in the market. And you'll notice in this image, the robots are so light that they're in fact portable. You see that they're, in this case, they put them on a frame on casters. So you could move the robot from station to station as the workflow dictated. That was brand new. And so that allowed for these robots to be seen in lots of new applications where the fence was gone and you had a robot possibly handing a piece of equipment or a part to its operator for inspection, etc., which is as we see here. Well, once the fence was lost, once you dropped that safeguard, now all of a sudden you see robots in lots of different industries. The Artis robot on your left is a collaborative robot after a fashion. This robot is actually used to harvest follicles of hair somewhere on your scalp and replant them elsewhere where they might be better served. Obviously a collaborative application because this robot is in direct contact with your head. And if you're going to use a robot of the collaborative variety to load and unload a machining center, there's not much difference between that and having it load a pizza oven. And so all of a sudden we start seeing robots in all kinds of explorations within food preparation. But this is the one that calls my attention. You can see that this collaborative robot is in a warehouse, and it has found a task it can do. It's erecting the boxes, the cartons. You see the magazine of cardboard, and this robot's job is to pull a carton out and push it through some process to erect the box, and then ultimately this will go through a taper and sealer. They found a repetitive task within the warehouse, and so this collaborative robot, where the operator can be right next to it safely, has found utility. But look in the background. You see all those shelves? Look at the variety of items on that shelf. Different size boxes, bags, items, etc. How do you deal with the variability there? Because that's really what the warehouse needs. And so collaborative robots, from the perspective of safe physical proximity, is not enough to deal with the variability that the tasks of the warehouse mandate. And that's why I talk about cognitive collaboration. Cognitive collaboration. I'm going to switch gears for a minute from evolutionary biology to developmental psychology. When children are growing, one of the sort of steps in their development is parallel play. You have children, they find a space, and she's coloring over here, and her friend is coloring over there, and as long as you stay over there, we're going to get along just fine. I do what I do, you do what you do. There's not a lot of interaction happening in parallel play. Well, I would argue this is a state of robotics and collaboration in the market. Generally speaking, you have a person and you have a robot, and the robot does a thing and the person does a thing, but there's not a lot of interaction between them. But just as with children, children grow from parallel play to cooperative play. Cooperative play means there's assigning of roles. You'll do this and I'll do that, and when you've done this, I'll do this. And there's communication and there's interaction. When you have cooperative play, it's always much more cognitive. It's decisions being made. And that's what the warehouse needs. Some of you may recall this robot. Speaking of Gil Pratt, this is from the DARPA challenge. And this was a challenge to sort of see what robots were capable of. And so you had all of these humanoid robots with lots of technology. This is a very sophisticated robot. And you can see the suite of sensors it has. It's got cameras and LiDAR, etc. And this robot, they had an obstacle course and they had a set of tasks the robot needed to complete. And so the robot did what it could autonomously. And maybe it ambled its way to this valve, and its sensors saw it, but they didn't understand what to do with it. And when that would happen, a remote operator could take control of the robot and say, that's a valve, and it works like this. And whether they teleoperated the robot or commanded the robot and the robot did it, locally, in either case, there was a human in the loop that stepped in when the autonomy failed. And that's the notion of supervised autonomy. And supervised autonomy is what the, sort of technical jargon in the literature is for what is cognitive collaboration. Let the robot do what it's able to do of its own volition. but then have a human step in for the sticky bits. And that's what you're going to need if you're going to deal with the great exploding warehouse. The warehouse of today is finding itself in a circumstance where the growth of e-commerce is burying their ability to keep up. We're all subscribing now, be it to razor blades, vitamin supplements, cat food. There's just more and more e-commerce coming online, and the warehouses have to keep up with all of this growth, and it looks kind of like this. This person's job is to take all of these parcels and packages and put them on the conveyor behind them. And it's a torrent. It's a never-ending flow of these packages into the system. So what do you need when you're dealing with that much variability? Well, the first thing you're going to need is a vision system. Just like that robot in the DARPA challenge, you have to have a set of sensors that can give some situational awareness and autonomy to the system. And so that's what Plus One builds. Plus One builds high-performance vision software for logistics robots. And this is what it looks like. Pick One is the vision system. It's a set of cameras, a set of sensors, and software, 2D, 3D, AI, and they're interpreting the scene in front of the robot, and through a set of heuristics, determining which is the next best thing to go pick. Obviously, Pick One is the bulk of the heavy lifting here. It's the autonomy in the supervised autonomy framework. So it can be 95, 99, 99.5% autonomous that the robot is working using that Pick One system. The Pick One system is, as you expect, 3D sensors and high-performance edge compute, including enterprise GPUs. But then there's this other component, the supervisory element of human in the loop, what we call Yonder. And we subscribe to this notion at Plus One because after 30 years as an industrial roboticist, I am convinced that people are better than robots at everything that matters here. And that's especially true of 3D vision and decision making. So when 99.5% isn't good enough, when the robot says, I don't understand, that's when it raises its hand over the cloud and a human sees exactly what that robot is looking at. And the human says, yep, I see the problem. I can see why that's so confusing. I would probably pick up this one. And you command the robot from remote, and the robot goes back to work. This notion of 3D vision plus human in the loop is the reason our company is called Plus One Robotics. Because through the addition of one human being into this control stack, you greatly increase the reliability, the fault tolerance of the overall system. And what that means then is you can have applications such as these. So in this case, you see the robot picking and placing parcels, and it's doing that of its own volition for most of the cycles, but then once in a while, this happens. And the robot sends a request to a crew chief. That's what we call the people on this end of the wire. And the crew chief says, oh yeah, I'd probably pick up that one. And as you see here, the scene is either very cluttered, like you see here, or it's occluded, as you see here, and the robot is able to deal with that because the human was able to command it. Here's another example. These robots are performing order fulfillment. You see there's multiple robots in this facility, and as the totes go by, the vision system is commanding the robot to go get the items out of the tote and put them in the shippable. But again, every once in a while, when you have hundreds of thousands of SKUs, the system will get confused. And this is what it looks like for a crew chief dealing with that situation. You see the robot requested support with a certain pick, and she was able to tell it, I use this tool and I picked that item, and the robot said thank you very much and went back to work. And finally, this is another implementation of hand-eye coordination you see everywhere in warehouses, depalletizing, taking boxes and bags and trays off of pallets and inducting them onto conveyors, etc. Same situation. You see that the bulk of the activity, the robot is working of its own volition, but right there, the robot is asking for help. And you see all of a sudden that the robot went back to work. Why? Because of the intervention of the crew chief. Pick one for autonomy, yonder for human-in-the-loop support. When I think about what this enables, it really does fill this middle portion of the autonomy spectrum. You know, on one side of the autonomy spectrum, you have Detroit. Motor City, tons of robots working on a line, high force multiplier. You know, it may be 200 robots on a respot line, and there may be just 2 or 3 people walking around cleaning welding tips. The system has a tremendous multiplier on labor, but it has next to zero flexibility. All the way on the opposite side of the spectrum, Intuitive Surgical and the Da Vinci. No force multiplier, 1 robot, 1 surgeon. But anywhere that robot can reach and any tool that robot has available to it, that surgeon can take full advantage of. No force multiplier, but effectively infinite flexibility. Supervised autonomy is in the middle. It isn't 200 robots to 1, but it may be 50. And so you have a crew chief that's able to manage a number of robots, but given the flexibility that they need to be able to deal with the tasks at hand. And that's the notion of supervised autonomy. In a system such as this, robotics is always a systems problem. You're going to have software, you're going to have compute, you're going to have the robot itself, grippers, cameras, etc. So some of the enabling tech that has to come together over the last 5 to 10 years to make this a reality, for one, is on the sensing side. And whether it's LiDAR, structured light sensors, time of flight, all of those sensors have come to bear on this problem over the last decade. The other, obviously, is the improvements in edge compute. Again, we use high-performance industrial PCs with NVIDIA enterprise GPUs to parse that point cloud and run the AI model at the edge. But of course, you have the human-in-the-loop piece, and that's a cloud connection. And over the last 10 years, we've been able to incorporate these cloud environments into the overall solution. I can tell you that just as users, warehouse operators have their preferences for robot suppliers, whether it's Fanuc or ABB or KUKA or Yaskawa or Universal, they likewise have preferences on their cloud provider. So whether it's AWS or Google Cloud or Azure, all of these have been brought to bear to make cognitive collaboration possible. And it's cognitive collaboration that unlocks all of these different applications to support the great exploding warehouse. Thanks for your interest. Robots work, people rule.